This is lecture 4H, and today we're going to talk about reactions in solutions. And if you want to cause a chemical reaction to occur between two solutes that are dissolved in different solutions, one technique we use is called a titration. This is in which one solution is used to analyze another. And titrations are exemplified by two particular types of equipment. One is a long, thin tube, which in the picture is holding the cyan-colored solution. That's called a burette. Usually, this container, this piece of equipment, holds a reactant of known concentration. Below that, we put an Erlenmeyer flask with a second solution, and usually this one contains some type of solution that has an unknown concentration, an unknown mass, something we're trying to figure out. And by opening the little stopcock valve that's on the burette, which is located right here, then we can drip drops of the cyan solution into the purple solution to allow the two to react with each other. And we can then determine, by techniques we'll see in a few moments, the concentration or the mass of something in that unknown solution. A most common type of titration is an acid-base titration. And in an acid-base titration, what we do is we use a strong base to completely neutralize an acid that may be in the flask below, or we use a strong acid in the burette to completely neutralize a base that's in the flask below. Whichever you put in the burette is usually the solution of known concentration, and we call a solution of known concentration a standard solution. So if we do an example, and let's say we take an acid that we don't know its molarity, we place it in a Erlenmeyer flask at the bottom, and we put a burette above it. If we want to do an acid-base titration, because our unknown is an acid, we're going to have to put a base into the burette. And what we do is we use a strong base if we're going to put that in the burette. And because it's a strong base, it would completely dissociate. So the strong base would be filled with hydroxide ions along with some counter ion, like maybe sodiums or potassiums, which actually wouldn't be involved in the reaction. If this sodium hydroxide solution is of known concentration, we call it a standard solution. So a titration is typically set up with a standard solution in the burette, and that component is going to be either a strong acid or strong base. In the flask below goes the opposite, base or acid, that you don't know something about. It can be either strong or weak. And when you drip the sodium hydroxide solution or the basic solution down into the flask below, each hydroxide ion here, and if we actually count them here and see, each hydroxide ion, when it drops into the flask below, will bump into the acid molecule, and the hydroxide, being a Bronsted base, will pull the hydrogen off of it, creating water, and the HA acid molecule will have turned into A-. So the reaction that occurs when we drip the contents of the burette into the flask is that the HA that's in the flask will eventually bump into the hydroxide ion that gets dropped into it. The hydroxide, being a Bronsted base, pulls the hydrogen off of the HA, creating A-, and you make a water molecule. We say we have neutralized one of the acid molecules when we do that. So here, if I drip one in, one hydroxide has gone into this flask now, and the HA is turned into an A-. So one of the four acid molecules has been neutralized. And what we want to do is we want to continue to add the hydroxide solution to the flask until every single acid molecule gets neutralized. So we'll drip another one in, and a second hydroxide will neutralize a second acid molecule. So now we have two A-. I have two more to go. I'll drip another hydroxide in there that will neutralize the third HA molecule. Now we have three A-, only one HA left. To completely neutralize the acid that was in the flask below, and it didn't matter whether that acid was strong or weak. There were still four acids in there originally, so you need four hydroxides to neutralize it. I'm going to put one more hydroxide in there. That's going to neutralize the final one. So we have added just enough of the sodium hydroxide solution to neutralize all of the acid molecules in the flask below. So when all of the acid has been neutralized, we call this the equivalence point of the titration. Now, the problem is, how do we know when we've reached the equivalence point? And the answer is, visually, we can't tell. So what we do is we add another component to the flask below before we start the titration. And that other component is called an acid-base indicator. Usually, it's a weak organic acid or base that happens to change color in acidic or basic solutions. The most common acid-base indicator that we run across is a weak organic acid called phenylphthalein. It has a complex formula, but I'm going to abbreviate it as HIND, IND for indicator, and H because it's an acid, it has a hydrogen on it. So if you put just one indicator molecule in there, as the hydroxides are dropping into the solution, they will neutralize the 4 acid molecules, so the 4 HAs turn into 4 A minuses. And now if you add one more hydroxide, that hydroxide will pull the hydrogen off of the indicator molecule, creating the anion IND minus. And this is why this particular compound, phenylphthalein, is an indicator, because HIND is one color, but when the hydrogen is removed, the IND minus ion has its electron arrangement change, it absorbs light differently, and now it actually presents itself as a color. It's actually a pinkish colored substance. So if I drop one more hydroxide in there, I pull the hydrogen off, the IND minus ion is created, the solution turns pink, and we stop our titration. Now, has this introduced a little bit of error? Absolutely. We really needed 4 hydroxides in order to reach the equivalence point, but we needed to use a 5th hydroxide to cause the hydrogen to be pulled off of the indicator to change color. That's a small error. If you imagine we have billions and billions and billions of HA molecules in there, and we only put a very small amount of the indicator, then the error is going to be a little bit not too big. It's going to be a small error. But anyway, that's what we do to determine the equivalence point of a titration. This is now technically called the end point because it's really not exactly the equivalence point, but it's when you stop the titration. So theoretically, we're trying to get to the equivalence point, but in a titration, we have to add a little bit extra of the sodium hydroxide to neutralize the indicator to cause it to change color, so we're actually reaching the end point. And that's the technique we're going to use when we actually are reacting stoichiometrically solutions with each other. Let's work some examples. Let's say we're trying to find the mass of sodium bicarbonate in an antacid tablet. An antacid tablet, by definition, reacts away acid in somebody's stomach, so the antacid tablet must contain something that reacts with acids, it must be a base. So the base that's in the antacid tablet is sodium bicarbonate. When you dissolve an antacid tablet in water, the sodium and bicarbonate ions separate from each other, and it's the bicarbonate ion that is a basic substance. So if we want to find out how much bicarbonate there is in an antacid tablet, then because that's a base, we can titrate it with an acid. So I will put an acid of known concentration, a strong acid of known concentration, in a burette, and I will take the sodium bicarbonate from the antacid tablet, dissolve it in some water, and place it in a flask below, and our setup will wind up looking like this. So the flask below would have the sodium bicarbonate dissolved in water, and that frees up the bicarbonate ions. And we have our acid molecule, or acid hydrogen ions rather, in the burette, because in the burette we put a strong acid like HCl, for example, and they would ionize, so there'd be chloride ions and hydrogen ions. And it's the hydrogen ions that are going to do the reacting. Each hydrogen ion here will react with the base of the bicarbonate. So this hydrogen ion will come down here and bond to HCO3 minus to form H2CO3. This hydrogen will bond with the second one to form H2CO3. This hydrogen will bond with the third one to form H2CO3. And when that happens, you will have neutralized all of the base ions in the solution. Now, how do we know when the reaction ends? We would have to use an indicator. So let's think about this. If we put an indicator in there like phenylphthalein, that indicator has its hydrogen pulled off by bases, and right next to it is an HCO3 minus. So if you're going to put an indicator into a basic solution, the hydrogen ion from the indicator will be pulled off by the base. The base will turn into H2CO3, and the indicator will form IND minus, and the solution will turn pink. So in a titration like this, your solution is actually pink. When you add a hydrogen ion now, the hydrogen ion will go down and react with one of the bicarbonates. So it'll react with this one to form H2CO3. The second hydrogen will react with the other one to form H2CO3. And when those are all gone, a third one will come down and react with the indicator to form HIND again, and the solution will turn colorless. So this is kind of an opposite titration. You start with a pink solution and you keep adding the acid until the solution turns colorless. So this is what we would do. So let's describe maybe an experiment which did this. Let's say the tablet, the antacid tablet, is dissolved in water, an acid-base indicator is added, and then it took 21.5 milliliters of a 0.300 molar hydrochloric acid solution. So it's a solution of known concentration. That's a standard solution. And that produces a color change to the indicator. In this case, the indicator would go from pink to colorless. So if we're going to try to calculate what the mass of the sodium bicarbonate was in the antacid tablet, we have to write the balanced equation. So we had sodium bicarbonate in the flask at the bottom, reacting it with hydrochloric acid. So these are our two reactants. Whenever you see two reactants, to predict the products, you switch the partners. Sodium goes with chloride, hydrogen goes with bicarbonate, and that would form NaCl plus H2CO3. H2CO3, you might recall, completely decomposes into water and CO2 whenever it's formed. So the actual products would be water plus carbon dioxide. Now to balance the equation, I have two hydrogens on the left, two hydrogens on the right, one sodium on the left, one sodium on the right, one chlorine on the left, one chlorine on the right, three oxygens, three oxygens. So this one happens to be balanced how it's written. So we're set to start. Much like when we were doing mass calculations a couple of lectures ago, when you do a chemical reaction problem and you're solving for something numerical about one of the reactants or products, this is chemical stoichiometry, you write down under each particular reactant product any information that's given in the problem. So in this case, we're trying to solve for the mass of the sodium bicarbonate, so I'm going to write X grams under that. For the hydrochloric acid, I know two things about it, and this is what's going to be significantly different between the mass-to-mass problems we did before and now solution chemistry problems. Whenever you're dealing with a solution, you have to know two bits of information, molarity and volume. And they've given us both of those in the problem. It's 21.5 milliliters of HCl was required to reach the equivalence point or the end point, and it's 0.300 molar. So in this reaction, the sodium bicarbonate and the HCl react in a 1-to-1 ratio. And so that's going to be the way I'm going to convert from my HCl numerical data into my sodium bicarbonate numerical data. So as you may recall, when you have solution data, and that solution data is the concentration in molarity and then the volume, the reason we use molarity in chemistry is because it makes it really easy to calculate moles. We just multiply the molarity times the volume. So my first step in the calculation is going to be multiplying the 0.300 moles of HCl per liter by 0.0215 liters of solution. Liters of solution cancel out. I've now calculated my moles of one of the reactants. If you think back to a couple lectures ago, when we're doing mass-to-mass calculations, what was always the first step? We switched grams of something into moles. So the generality is your first step in a stoichiometric problem is always convert whatever you're given into moles. So if you're given grams, you convert it into moles with the molar mass. If you're given solution data, you convert it into moles by multiplying molarity times volume. What's the second step? Once you've calculated moles of one of the reactants or products, now you can use the mole-to-mole ratio in the balanced equation to convert from one substance to another. So in this chemical reaction, 1 mole of HCl reacts with 1 mole of sodium bicarbonate, so I'm going to multiply it by that ratio, written appropriately so that I can cancel out the moles of HCl, and now I know how many moles of sodium bicarbonate must have reacted with it. This is therefore how many moles of sodium bicarbonate must have been in the antacid tablet. If I now want my final answer to be in grams, I switch moles into grams by using the molar mass of sodium bicarbonate. And if I multiply it with the mole fraction of it on the bottom and the mass on the top, the moles will cancel out, and I will now have calculated how many grams of sodium bicarbonate must be in that antacid tablet. It's a little bit over half a gram. Let's try another example. Let's say we have an aluminum hydroxide solution, and we want to know what its molarity is. Okay, so we're going to try to find the molarity of aluminum hydroxide solution. Okay, if we picture how we would do this, because the aluminum hydroxide solution is what we're trying to figure out, we would put that in the flask at the bottom and it would dissociate. We would have lots of hydroxide ions floating around in there. What would react with a base? An acid. So I would take another strong acid, probably like HCl again. I would put it in the burette, and we would have to know its concentration. It would have to be a standard solution. So in this case, if I have 5 hydroxides down here in my flask, I'm going to need 5 hydrogen ions to react with it. And if I want to see when the reaction is going to end, I'm going to have to put a drop of indicator solution in there. So we'll actually need to have 6 hydrogen ions neutralize all 6 of the substances in the flask. And that way that's going to, or actually it'd be a little bit different in this case. What's going to happen is the hydroxide, one of these hydroxides, will then pull the hydrogen off of the indicator, just like in the one before. That's going to turn pink as we form water and IND minus. So now we're going to need 4 of the hydrogen ions from the burette to react with the 4 hydroxides, 1, 2, 3, 4, and then a 5th one will react with the indicator to form HIND, turning it back to colorless. We'll have the end of our titration. So here's a description of how we would do that. Let's say an acid-base indicator is added to 10.0 milliliters of the aluminum hydroxide solution, and then it wound up taking 12.5 milliliters of 0.300 molar hydrochloric acid to produce a color change to the indicator. So we've got our setup on the right. Let's write the balanced equation so we can do our stoichiometry. The reaction is between aluminum hydroxide and what's in the burette, which is the hydrochloric acid. So when these react, 2 compounds, they're going to switch partners. Aluminum is going to go with chloride to form AlCl3, and hydrogen is going to go with hydroxide to form HOH or water. When I do exchange reactions that form water, I like leaving the water as HOH because it makes it easier to balance. You can see I have 3 hydroxides on the left side of the equation. So if I put a 3 here, that puts 3 hydroxides on the right side. That now makes 3 hydrogens on the right side that aren't in the hydroxide ion, 3 free hydrogens. So to get 3 free hydrogens on the left side, I'll put a 3 in front of the HCl, and that actually also balances the chlorides. So this is our balanced equation. Let's write down what's given and what we're trying to figure out. In this case, they tell us we have 10.0 milliliters of the aluminum hydroxide solution, but they want to know its molarity. So because it's solution data, I have to write down 2 things, molarity and volume. But in this case, one of those is what we're solving for. So I write X molarity, but I have to include 10.0 milliliters. For the hydrochloric acid, it's solution information, so I have to write down both molarity and volume for it. It was 12.5 milliliters, and we had a concentration of 0.300 molar. The important ratio in this balanced equation, this is why we write the balanced equation, is so we know what the relationship is between aluminum hydroxide and hydrochloric acid. And the coefficients in the balanced equation say 1 mole of aluminum hydroxide requires 3 moles of hydrochloric acid to react with it. This is the setup to the problem. So you always start with data that you can convert into moles. And I can't convert the aluminum hydroxide information into moles because there's a big old X underneath that. So I've got to start with the hydrochloric acid information. And because it's solution data, I calculate moles from solution data by multiplying molarity times volume. So we're going to start this by going 0.300 moles of HCl per liter, multiplied by the volume converted to liters, 0.0125 liters. Liters cancel out, and that's the first step in all stoichiometric conversions, or you calculate how many moles there are of one of the reactants or products. Once you've done that, the second step is always convert from moles of that substance to moles of the one you want, which is in this case the aluminum hydroxide. So I'm going to multiply by the mole ratio in the balanced equation with the HCl on the bottom, the aluminum hydroxide on the top, and this will tell me how many moles of aluminum hydroxide must have been in that solution in the flask. If I want to calculate the molarity of the aluminum hydroxide, now I think about the definition of molarity. It's moles per liter of solution. I have moles of aluminum hydroxide, so all I need to do now is divide by the volume of the aluminum hydroxide solution you originally had, which was the 10 milliliters. So you can multiply this out, get an answer right now, and then divide by 0.0100 liters, or you can do it all in one step. Dividing by 0.0100 liters is the same thing as multiplying by the reciprocal of 0.0100 liters. So if I do it like this, I'm not going to have any rounding errors by having to do 2 calculations and keeping a guard digit. So if I do it all in one calculation on my calculator, no rounding errors whatsoever, And each of the measured numbers in the problem are 3 significant figures. So my answer will come out 3 significant figures, 0.125 molar aluminum hydroxide. That makes sense. Why don't we have you try to do one on your own very similar to that? Let's have you calculate the molarity of a sulfuric acid solution if 25.0 milliliters of it are neutralized by 33.5 milliliters of a 0.240 molar potassium hydroxide solution. And if you want to pause this then for a moment, do the calculation, and then when you come back, we'll go through the procedure for that. So in this reaction, we're reacting potassium hydroxide with sulfuric acid. So we'll have to try to write the balanced equation. Now, what's actually happening? We have the sulfuric acid in our flask at the bottom because that's what we don't know. We put a known concentration of a strong base in the burette, and in order to know when the equivalence point of the titration is, we're going to put an indicator in there. So in this case, the solution is going to be colorless at first, and then the hydroxide ions will come down, and each hydroxide will neutralize an acid, an acid, an acid, an acid, and then a fifth one will pull the hydrogen off of the indicator, and that's going to turn the solution pink. So that'll happen as we do the reaction between the sulfuric acid and the potassium hydroxide. Two compounds switch partners. Hydrogen with hydroxide makes water. Potassium with sulfate makes the salt K2SO4. To balance this, I have two free hydrogens on the left side. So to get two free hydrogens on the right side, I'll put a 2 in front of the water. That makes two hydroxides now on the right side. So to get two hydroxides on the left, I'm going to put a 2 in front of the KOH. Now my equation is balanced because I also have then one sulfate, and two potassiums. Let's write down what's given and what we're trying to figure out. They told us we put in the flask below 25.0 milliliters of a sulfuric acid solution that we don't know its molarity. We used 33.5 milliliters of potassium hydroxide to neutralize it. Its molarity was 0.240. The mole ratio in the balanced equation between these two reactants is 1 to 2. First step, convert given information into moles, and we can only convert the potassium hydroxide information into moles. So I'm going to multiply its molarity, which I'm going to write out explicitly as 0.240 moles of KOH per liter. You can't write 0.240 or 0.240 capital M, because capital M isn't a unit, it's an abbreviation. It stands for moles per liter. So if you write it out explicitly, when you multiply it by the 0.0335 liters, now you can see the liters canceling out. This is why you've calculated moles. Second step, mole ratio. In this balanced equation, 2 moles of KOH react with 1 mole of sulfuric acid. Moles of KOH cancel out if you put the KOH in the bottom. And then if you now want to know what the molarity is, we already have moles of H2SO4. You have to divide by its volume or multiply by the reciprocal of its volume. So if we multiply by 1 over 0.0250 liters, the units come out, moles per liter, and you'll now have the molarity of the solution. Each number that's a measurement in the problem is a 3 significant figure number. So the answer will come out 3 significant figures, and I get 0.161 molar sulfuric acid. Now, when you do acid-base titrations, and we're going to put either a potassium hydroxide or a sodium hydroxide solution into a burette, what we always do is we have to calculate the molarity of the sodium or potassium hydroxide right before we do the titration. That's called standardizing the solution. Why do we have to do that? That's because there's a lot of carbon dioxide in the atmosphere of the Earth. And when carbon dioxide dissolves into any liquid, any water, it actually turns into a small amount of carbonic acid. So if you prepare a sodium hydroxide solution on Monday and you leave it out for a couple of days on Monday night, Tuesday night, Wednesday night, carbon dioxide is going to dissolve into that, create a little bit of carbonic acid, and the carbonic acid will react away some of the hydroxide ions. The concentration will go down. So it changes with time. So the day you're going to do a titration, you've got to see what is the concentration of that sodium hydroxide or that potassium hydroxide solution right then at that instant, take into account that some of it has reacted away because of the carbon dioxide in the air. So the way we usually do this, the way we standardize a solution, is we put the sodium hydroxide solution in a burette, and we drip it into a flask that has a known mass of some solid acid. So a way we might do this is we might take 34, or let's say we put some solid acid into a flask at the bottom, and it took 34.2 milliliters of the sodium hydroxide solution to neutralize a solution that we made with 0.619 grams of solid H2C2O4.2H2O. That compound is called oxalic acid dihydrate, whose molar mass happens to be 126.08 grams per mole. Let's look at a picture of this. Sodium hydroxide solution in the burette that I'm trying to determine its molarity. I've now stuck, can you see that big old crystal down there of oxalic acid dihydrate? Instead of writing H2 and then C2O4.2H2O, I just made that all an X. So I wrote it H2X. So there's 4 oxalic acid dihydrate molecules in that. I put the crystals into the flask. I weigh the crystals. Their mass was 0.619 grams. And then I add a bunch of water. And when I add a bunch of water to it, the crystals will dissolve and they'll start floating around in the solution as individual acid molecules. And now it's very similar to the titrations we've seen before. We're just going to add the hydroxides to this in order to neutralize all the hydrogens. In this case, each hydroxide only neutralizes 1 hydrogen. So if you actually want to count them up, then we would actually need 2 hydroxides to neutralize this, 2 hydroxides for that, 2 hydroxides for that, 2 hydroxides for that. So I'm going to have to add 8 hydroxides to neutralize all the acid in this particular flask. Now, how much water did they put in there? They dissolved it in water. Well, it doesn't matter. Look at this. You have 4 oxalic acid dihydrate molecules in there. What if I would have added more water? How many molecules are there? There's still 4. You still need 8 hydroxides to neutralize it. So as long as you weighed out the mass of the crystal, 0.619 grams, then you're going to be able to determine the moles of the oxalic acid from that mass. And it doesn't matter how much water you put in there, it's still going to be the same number of moles of oxalic acid dihydrate. Of course, we'll put an indicator in there, so we'll actually need 1 more hydroxide to neutralize the indicator to make it turn pink. So let's see how this calculation works. The reaction is between sodium hydroxide and oxalic acid dihydrate. You have never seen a reaction between 2 compounds in which one of them is a hydrated substance. So here's how you do this. You see the .2H2O? Pretend it's not there. Now you can write a balanced equation, switch the partners. Sodium's going to bond with oxalate, +1 - 2 will form Na2C2O4, and hydrogen will go with hydroxide to make HOH. Now let's balance it. There's 2 sodiums on the, how am I going to do this? Which one do I want to do first? 2 hydrogens on the left? No, I'll do the sodiums first. So 2 sodiums on the right. So let's make 2 sodiums on the left by putting a 2 here. That now makes 2 hydroxides and 2 free hydrogens on the left. We need to put a 2 in front of the water. And now we have a balanced equation. That's not so bad. Now we have to remember the oxalic acid was a dihydrate. So I'm going to stick the 2 water molecules back onto the H2C2O4. But if I do that, I'm going to unbalance the equation. So if I stick 2 more water molecules here on the left side, guess what I have to do to make sure the equation stays balanced? I have to add 2 more water molecules to the right side. And I already have 2 there, so I got to switch the 2 to a 4. And that's how you balance an equation that has a hydrated reactant in it. Let's write down what's given and what we're trying to figure out. We're given 0.619 grams of oxalic acid dihydrate. We weighed out the crystal, we put it in a flask, then we added a bunch of water so that it dissolved. I don't care how much water, we know how many grams of the oxalic acid dihydrate we used, 0.619. We can convert that into moles with its molar mass, so the amount of water in the solution is completely irrelevant because I don't have to use that value, that volume of water, in any of my conversions. For the sodium hydroxide, it's solution data. We got to put 2 bits of information down, volume and molarity. So we know what volume was required to neutralize it, and the molarity is what we're trying to solve for. The mole ratio in this problem are the coefficients in the balanced equation, 2 to 1. So to do the calculation, first step is to always start with whatever substance you can convert its data into moles, and that's the oxalic acid dihydrate. So I'm going to take the 0.619 grams of OAD, oxalic acid dihydrate, convert it into moles. Just so you know where this molar mass came from of 126.08, I added up the masses of 2 moles of hydrogen, 2 moles of carbon, 4 moles of oxygen, and then 2 moles of water, 218.02. So when you have a hydrated substance, because those waters are actually in the crystal, you've got to calculate the molar mass of the entire thing. So if you check that to make sure that I've done it correctly, that should come out 126.08. So I'm going to use that molar mass to convert the grams into moles by putting the 126.08 grams on the bottom to cancel out and mole on the top. And that allows us to go to the second step, which is going to be the mole ratio in the balanced equation. 1 mole of oxalic acid dihydrate on the bottom, 2 moles of sodium hydroxide on the top, and now we've figured out how many moles of sodium hydroxide were in the 34.2 milliliters that we dribbled into the flask. If I want to know the molarity of that sodium hydroxide, I'm going to divide it by the volume, which was the 34.2 milliliters, so 1 over 0.0342 liters, and that's going to wind up giving us the molarity of our sodium hydroxide solution of 0.287. And so now we can do titrations with the sodium hydroxide solution for the rest of the day, and we can feel assured that the molarity is known to be 0.287. Now, one other type of calculation you can do with an acid-base titration is you can calculate molar masses of acids. Specifically, if you have a solid acid, you can calculate its molar mass. We were doing molar mass calculations with colligative properties on our last test. So now here's another way for you to calculate the molar mass of some solid substance. If somebody just hands it to you in lab and they happen to tell you it's an acid, you can actually figure out the molar mass of that solid acid. So we're going to try to calculate the molar mass of a diprotic if 0.409 grams of it are neutralized by 19.50 milliliters of the 0.287 molar sodium hydroxide solution that we just standardized. Okay, what does diprotic mean? Protic refers to a proton. A proton is a hydrogen ion. And in relation to acids, what do acids have in their formula? Hydrogen ions. So if you have something like HCl that has 1 hydrogen in its formula, we call it a monoprotic acid. But if you have something like sulfuric acid, H2SO4, that has 2 hydrogen ions in its formula, that's what a diprotic acid is. So they're telling you that this unknown acid must have 2 hydrogen ions in its formula. Phosphoric acid is a final example, H3PO4, that would be called a triprotic acid. So if we don't know what the acid's formula is, but we know it has 2 hydrogens in it, I'm going to write it as H2X. And so in my balanced equation, I'm going to say, okay, H2X is being neutralized by NaOH. And how are we going to wind up getting the molar mass of this H2X? Well, think back to how you got molar masses back in the colligative property chapter. You would have to know 2 things about H2X. You would have to know its mass and its moles, and you would have to divide them. So we need to know the grams of H2X and divide it by the moles of H2X. And what we do in the first step of our experimental procedure here is you actually take the solid acid crystals and you weigh them on a balance. So we know 0.409 grams of it. So you're going to do the titration to solve for the moles of H2X. So our final step, once we calculate moles of H2X, is we're going to place the moles of H2X where the question mark is, divide, and that'll be the molar mass. And that's how you calculate the molar mass for an acid from a titration. So let's see if we can solve for the number of moles. The reaction is going to be our diprotic acid H2X with the sodium hydroxide. We're just going to switch the partners. H goes with OH to make HOH, and then Na goes with X. And let me give you a little hint about something if you're going to wind up taking the MCAT someday, because this is the type of question they're going to put on there. They're going to give you these 2 compounds like this, and they're going to tell you or ask you, what's the formula of the compound between Na and X? And they don't expect you to have memorized charges and polyatomic ions from years past, but they'll expect you to look at this and go, if hydrogens are +1 each, and there's 2 of them in the formula of this acid, then if they're +1 each, guess what the charge of X must be? Has to be -2. So if it's going to bond with a sodium, which is +1, if that's +1 and that's -2, then the formula would have to be Na2X. Okay, that's conceptually what they want you, a doctor, to be able to figure out from bits of information here. So you should be able to figure out the formula would have to be Na2X in this example. To balance the equation, because I have 2 hydrogens on the left side, I'll put a 2 in front of the water on the right. And now that gives me 2 hydroxides on the right, so I'll put a 2 in front of the NaOH, and that now balances the sodiums. So now we have a balanced equation. Let's write down what's given and what we're trying to figure out. We know 0.409 grams of the diprotic acid. What are we trying to solve for? In order to get the molar mass, you have to solve for the moles of H2X. And so I'm going to write that down here. 0.409 grams of H2X, I'm solving for moles. What are we given? We're told it took 19.50 milliliters of the 0.287 molar sodium hydroxide to neutralize it. So I'm going to try to work this problem until I can solve for moles of H2X. The important relationship from the balanced equation, 1 mole of H2X reacts with 2 moles of NaOH. Start the problem with whatever you can convert into moles. You cannot convert 0.409 grams of H2X into moles because you don't know its molar mass. You have to start with the sodium hydroxide data. There's no other choice. So take its molarity and multiply it by its volume. When we do that, the liters of the solution will cancel out, and you will have calculated how many moles of sodium hydroxide were used for the reaction. Now do the mole ratio in the balanced equation. It's a 2-to-1 ratio. 2 moles of sodium hydroxide on the bottom, 1 mole of H2X on the top. Moles of sodium hydroxide cancel out. Our units now are moles of H2X, and that's what we're solving for. You're done. There actually isn't a third step in this calculation. So multiply this out, a 3 significant figure number by a 4 significant figure number will give you a 3 significant figure answer, and then I'll keep a guard digit. So we've determined the number of moles of H2X, and much like in all of your colligative property calculations, when you did the last step to determine the molar mass of an unknown, you have to know the grams of the unknown and divide it by the moles of the unknown. So we take the 0.409 grams of the H2X, we divide it by the 0.002798 moles of the H2X, and I will get grams per mole, and that'll be a 3 significant figure answer, and that's going to be the molar mass of this diprotic acid. Now, we've done a lot of examples today of acid-base titrations, but you can also do a titration between something that is oxidized and something that's reduced, and these are called oxidation-reduction titrations, and I want to try a couple of examples of those. So let's say a 10.0 milliliter aliquot of a solution containing vanadium positive 2 ions is acidified, and 32.7 milliliters of a 0.115 molar permanganate ion solution produces a light purple color. If the vanadium positive 2 was oxidized to vanadium positive 5, determine the molarity of the vanadium positive 2 in the original solution. So before we start, let's just identify this word aliquot. That's a fancy way of saying a sample of a solution. So a 10.0 milliliter sample of a solution containing vanadium 2 ions is how that's read, but if you want to be fancy, you call it an aliquot. So we're trying to figure out the concentration of the vanadium 2 ions. So in a titration, I would put that in my flask at the bottom. I need a known concentration solution that's going to react with that. And vanadium ions aren't acids or bases, so I can't pick an acid or base to react with it. But if vanadium positive 2 could be oxidized up to vanadium positive 5, I could react it with an oxidizing agent, and permanganate's a really good oxidizing agent. So the permanganate would react with the vanadium plus 2. To figure out what happens, let's do the oxidation numbers. In permanganate, oxygen is -2. There's 4 of them. They add up to -8. So the manganese must be +7. And then we know vanadium is just equal to its charge +2. Well, they said the solution was acidified. That means they probably put a couple of drops of acid into the flask at the bottom. So when the permanganate drops into there, it's going to do a reduction in an acidic solution. And we've learned that manganese gets reduced from +7 down to +2 in an acidic solution. So that's a reduction. So the permanganate gets reduced, it's going to make something get oxidized, and the problem told you what happens because you may not be able to predict this, but the vanadium plus 2 would be oxidized up to a higher oxidation state of +5. This is an oxidation reduction reaction. So the way you'd set that up is you would put the solution with the vanadium ions, the vanadium 2 ions in the bottom, and you would put in your burette the potassium permanganate, which I've labeled here as purple. You may remember from our oxidation reduction experiment that permanganate has a characteristic purple color. So what we're going to do is we're going to drip the permanganate down into the vanadium positive 2 solution, and we're going to add enough permanganates until every single one of these vanadium positive 2 ions turns into a vanadium positive 5 ion. So let me do that. Pink, there we go. So now all the vanadium positive 2s have changed into positive 5, and we added a certain amount of this, okay? Now, how do we know when you reach that point? Well, we don't. So what you do is you add one more drop of the permanganate solution, so one more permanganate goes down into the flask below. You see permanganate's purple. When the permanganate gets changed into manganese 2, the purple color goes away, so the solution has stayed colorless. But if you don't have any more vanadium 2 ions here, there's nothing for the permanganate to react with, so when you put one more drop of permanganate in there, the solution will show a light violet color. That's when you stop. So the permanganate itself is the indicator because it causes the solution to change color once it has nothing to react with. So for us to be able to do this calculation, we need to write a balanced equation. And I have not balanced my oxidation reduction reaction, so let's go ahead and do that. I want to write my oxidation and reduction half reactions. So the oxidation half reaction is the permanganate turning to Mn2 plus. The oxidation, that's the reduction. The oxidation half reaction is vanadium 2 going to vanadium 5. Let's balance them. Top reaction, all non-oxygen hydrogens are balanced. That's fine. Second step, balance the oxygens by adding waters. I'll need 4 waters on the right. Next step, balance the hydrogens by adding hydrogen ions. I'll need 8 of those on the left. Last step is to put electrons in by doing the charge. There's 8 positives and 1 negative. This side has a charge of positive 7. This is plus 2 and 0. This side has a charge of plus 2. 7 doesn't equal 2. I need 5 extra electrons on the left side. For my second half reaction, the vanadiums are balanced. There are no oxygens or hydrogens, so all I have to do is balance the charge. And because my higher charge is on the right, plus 5 is higher than plus 2, I need to add 3 negative electrons to the right side to bring that charge down to 2. And now we have 2 balanced half reactions. In order to add them together, we have to make sure the electrons gained and lost are equal. And I have a 5 electron change and a 3 electron change, so I'm going to find a common multiple of 15. I'm going to multiply the top reaction by 3, the bottom reaction by 5. So multiplying the top reaction by 3, this will become 15, 24, 3, 3, and 12. And the bottom reaction will become 5, 5, and 15. And now I'll have 2 reactions where the number of electrons gained and lost are exactly the same. So now I can add these together. And if I do that, I put all the reactants on the left side, so the 15 electrons, the 24 hydrogen ions, the 3 permanganates, and the 5 vanadium 2s, and all the products on the right side, the 3 manganese 2s, the 12 waters, the 5 vanadium 5s, the 15 electrons, and we can now cancel out the 15 electrons. And when we've done that, we now have our balanced equation for what's taking place during this titration. So here's the reaction with the 15 electrons canceled out. Now we're ready to start the problem. We're going to write down what's given and what we're trying to figure out. We're told that we used 32.7 milliliters of the permanganate solution and its molarity was 0.115. We're trying to solve for the molarity of the vanadium ions, and we know the sample we put into the flask was 10.0 milliliters. The mole ratio in this balanced equation, this is why we balanced the equation, 3 moles of permanganate react with 5 moles of vanadium 2. First step in all solutions, actually first step in any chemical reaction stoichiometric problem is to convert some given information into moles. If you're given grams, you convert it into moles with the molar mass. If you're given solution data, you go molarity times volume. So I'm going to take the molarity of the permanganate, 0.115 moles per liter, multiply it by its volume of 0.0327 liters. This will give me, oh, I put the line in the wrong place. That should have been the liters on the bottom that canceled out. So we will get moles of permanganate, so just pretend that line was a little bit lower. Second step, mole ratio in the balanced equation. To cancel out the moles of permanganate, 3 moles of permanganate on the bottom, 2 moles of vanadium 2 ions on the top, cancel out the moles of permanganate. Now they're canceled out. And we now have moles of vanadium 2. If we want to get the volume, or rather the molarity of the vanadium 2 solution, I'm going to divide by its volume. So you divide by the 0.0100 liters, and that's going to wind up giving you the molarity of the vanadium-2 solution, which comes out to be 0.627 molar. So we can do titrations that are oxidation reduction as well as acid-base. And let's do one more oxidation reduction titration. Cinnabar ore contains sulfide ions. A 1.534 gram sample of this ore is dissolved in acid. Then all of the sulfide is oxidized by 20.4 milliliters of a 0.110 molar dichromate ion solution. Determine the percentage of sulfide in the cinnabar ore. So here's a couple things you're going to have to start thinking about when they're asking you to get percentages of one substance in another. They want the percentage of sulfide in cinnabar ore. So you're going to have to calculate the mass of the sulfide so that you can divide it by the mass of the cinnabar ore and multiply by 100 to make the percent. So this problem, you're going to be solving for the mass of sulfide ions. Cinnabar ore is not in the equation. Cinnabar ore is a rock. It's actually an orangish colored rock. If you ever go to the Natural History Museum up at USC in Los Angeles, you go into the geology section there and you can see the cinnabar ore, beautiful looking crystals. And it's a nice orange color, but it's a rock. And so it contains sulfide. So a rock is not a pure chemical. It's a mixture of lots of different things. And you're trying to find out how much sulfide is in that. So the reaction that's going to take place is not cinnabar ore plus something. It's the component that will react in the cinnabar ore. It's the sulfide ions. So the sulfide ions are the ones that are going to be reacting with the dichromate. So a lot of this beginning stuff is fluff. It says the sample of the ore is dissolved in acid, and that's just telling you how they're taking the ore, they're turning it into a solution, so the sulfide ions are freely floating around, and now you can drip in the dichromate ions to react with it. So the reaction is going to be the potassium dichromate solution with the sulfide ions. I wrote potassium dichromate. I probably should have written that up here in the problem, 0.110 molar potassium dichromate, because I'd actually want to write it in ionic form. So maybe if we skip the first line and just imagine these are the two reactants, because this sort of goes along with what the problem says. So dichromate ions are reacted with sulfide ions. This is an oxidation reduction reaction. And to predict what's happening, we need the oxidation numbers. So the potassium +1, the oxygens are -2 each. They add up to -14. So the chromiums must add up to +12. So each chromium must be +6. And then the sulfide ion is -2. Dichromate is a strong oxidizing agent. We know it gets reduced into chromium 3. So its charge is going down. You have to find an element whose charge can go up. And the only element whose charge can go up is going to be the sulfide. Negative anions of nonmetals get oxidized up to their elemental state. So the sulfide is going to be turned into sulfur, which exists as octaatomic molecules. So the titration is going to be dripping in the dichromate ions into the solution of sulfide ions and other stuff. The dichromate will turn into chromium 3, and the sulfide will change into elemental sulfur. To balance the equation, we're going to write the two half reactions, dichromate turning into chromium 3 and sulfide turning into sulfur. Let's balance them. First, balance the non-oxygens and hydrogens. So the first reaction, I need to put a 2 in front of the chromium on the left side, or right side. Balance the oxygens with waters, so I'm going to need 7 waters on the right side. That puts 14 hydrogens on the right side. I'll need 14 hydrogen ions on the left side. The charge is now +14 and -2. That adds up to +12. This side adds up to +6. The difference between 12 and 6 is 6. I need 6 electrons on the left side. For the sulfur half reaction, there's 8 sulfurs on the right, so I need to put an 8 in front of the sulfide on the left. There's no oxygens or hydrogens, so all the elements are balanced, but the charge on the left side is -16. The charge on the right side is 0. So I'm going to need to put 16 electrons on the right side to balance the charge. These are my two half reactions. If I want to add them together, I need to find a common multiple between 16 and 6, and I believe that is 48. So in order to get 48 on each side, I'm going to multiply the top reaction by 8 and the bottom reaction by 3. So this is going to turn out to be some whopping numbers. It's going to be 48 electrons, 112 hydrogens, 8 dichromates, 16 chromium 3s, and 56 waters. And down below, it's going to be multiplied by 3, 24 sulfides, 3 S8s, and 48 electrons. So if I multiply those out, we get these numbers here, and now we can add the two half reactions together. So the left side will be the 48 electrons, the 112 hydrogen ions, the 8 dichromates, the 24 sulfides, and on the product side will be 16 chromium 3s, 56 waters, 3 sulfurs that are S8, and 48 electrons. Yeah, these numbers can get kind of wild. Sometimes that happens. Don't be freaked out when it does. So if you cancel out the 48 electrons, we now have the balanced equation. Now we're ready to start the problem. So here's our balanced equation, and we're going to write down what's given and what we're trying to figure out. We used 20.4 milliliters of the dichromate ion solution. Its molarity was 0.110 molar. We're trying to solve for how many grams of sulfide there are. Why are we trying to solve for that? Once again, if you're trying to determine the percentage of sulfide in cinnabar ore, we need the mass of sulfide and divide it by the mass of the cinnabar ore. We already have the mass of the ore, so we need the mass of the sulfide, so that's what the titration is allowing us to solve for. The mole ratio in this balanced equation between dichromate and sulfide is 8 to 24. So start your calculation with whatever data you can convert into moles, and that's going to be the solution data for the dichromate ions. Multiply its molarity times its volume, and that'll cause the liters to cancel out, and that'll give you moles of dichromate. Second step, mole ratio. Cancel out the dichromate by putting 8 moles of dichromate on the bottom and 24 moles of sulfide on the top. Moles of dichromate cancel out. Now you have moles of sulfide. Final step, you want to convert moles of sulfide into whatever you're looking for. What does it want you to solve for? Grams. So we switch moles into grams by using the molar mass. So go to the periodic table, get the molar mass of sulfur. That'll be the same molar mass as sulfide, 32.07. And arrange it so the moles of sulfide cancel out. And if you multiply this out, that's going to tell you how many grams of sulfide must have been in that 1.534 gram sample of that cinnabar ore. And that comes out 0.215, and then with a guard digit 9 grams of sulfide. So whenever you're doing percentages are always fractions. There's something divided by something else, and it'll tell you exactly how to do that. When it says sulfide in cinnabar ore, this is read sulfide divided by cinnabar ore. So take the mass of the sulfide divided by the mass of the cinnabar ore. And if you divide that, you'll get a fraction. That's the fraction of the ore by mass, that's sulfide. And if you want it to be a percent, you multiply by 100. So when you do that, we get 14.1%. And so therefore, the cinnabar ore must be 14.1% sulfide by mass.